Now, the reliability factor Kc, generally it depends on the reliability which we generally consider for designing of the component. So, for designing purpose we need to consider some reliability factor, it can be 50%, it can be 60%, 70%. So, depending upon this reliability value, generally we need to consider a factor that is called Kc. So, here we have provided a table which is a well standard table. This table generally here you see for rotating beam specimen, whatever the reliability percentage we consider, that reliability percentage is considered as 50%. So, that is why here the Kc value, if the reliability is 50%, their Kc value is considered as 1. Now, if the reliability you consider higher side, like here I have shown, higher the reliability percentage you can say for designing, lesser will be the Kc value and lesser will be the endurance strength. This you should keep it in mind. Like for 90% of reliability, you see your Kc factor is reducing 1 to 0.897. If it is 95%, you see further it is reduced. If it is 99.99%, if you consider, then it is its value is 0.702. If it is 99.999%, its value is generally considered as 0.659, you see. So, higher the reliability percentage, lesser will be the Kc value and lesser will be the endurance strength. Generally this table which is shown here, this table generally based on, you see, 8% you can say a standard deviation of the mean value. Okay. Why? Because generally this standard deviation of endurance limit test for rotating beam specimen generally is considered as 8% of the mean value. That is why the reliability factor which is showing here, here we consider the standard deviation of 8% of the mean value. This you should keep it in mind. So, how it is varying for different types of percentage of reliability for design consideration, that is showing here. So, this value we need to use when we go for design a actual component. Okay. Now, temperature factor which is called Kd. So, we know this temperature have a significant effect on what is called yield stress as well as ultimate stress value. You know very well, because what happens, this I have already discussed in the lecture of CREEF related fundamentals. Generally what happens, your yield stress, ultimate strength with increasing of temperature, both the things generally it is decreasing. So, here I am showing a standard data for steel material, you see steel material. This top curve generally represent ultimate stress and this horizontal axis represent temperature in degree centigrade, you can see. So, at room temperature, here you see RT represent room temperature, yield stress curve, yield stress or you can say yield strength curve, and this top one is ultimate strength curve. What you can observe from this figure, that if we increase the temperature, you see from room temperature, this ultimate as well as generally yield stress is gradually decreasing in nature, you can see. Whereas, generally this ultimate stress for steel material, it is observed that generally its reach some particular value for particular range of temperature. After that generally it is declined and it is gradually further decrease very rapidly, you can say, with further increase of temperature. This you can observe here. So, as this ultimate strength as well as you can say yield strength is decreasing with what is called temperature, that is why a separate factors generally we need to consider for endurance strength calculation if that actual specimen is subjected to some different temperature. If it is room temperature, then fine. If it is room temperature, then you can consider this Kd value equal to 1. But if it is different temperature range, then what happens, its value will be different. That is why generally you see a fourth order a fourth order temperature, you see this temperature equation is established for this temperature factor K d, which is shown here, you can see, where this temperature T is in degree Fahrenheit. This is in degree Fahrenheit, and the range of the temperature which is showing here, this is varying from 70 to 1000 degree Fahrenheit. Okay. This what is the Tf is showing, this Tf is actually in degree Fahrenheit. So, based on this equation you can easily find out what is the Kb value. Apart from these things, you can use another equation for finding out the Kd value, because at a particular temperature, if you know this ultimate strength, if you know the ultimate strength at a particular temperature, that ultimate strength divided by what is called room temperature ultimate strength, is generally, this ratio is called Kd value. So, this equation or this fourth order polynomial curve fit equation, both the equation you can use for calculating the Kd value. So, this Kd value, this equation you can use for any types of material, and this equation generally here which is showing, this is generally showing for this steel material. Here you see these data generally where which here we have plotted, this data is plotted for a experiment set of experiment is around 145 experiment set generally we use, and this is plotted, and we tested this data for different range of temperature. Apart from this thing, this equation also directly you can use. Here also you can observe that this Kd value always it should be less than equal to 1, because if because we know this St value generally always you see less than always generally decreases if the temperature is increases. Here you see here whatever the data I am showing, this is the data generally which is the temperature dependent data for, I have already told you, for 145 test for carbon and alloy steels at a different temperature, how it is varying, that things here it is showing. Okay. So, always you need to consider either Kd, that polynomial equation, or you can use Kd for what it is called the St, that means ultimate strength at a particular temperature by what is called at room temperature, whatever the ultimate strength is there, that ratio also you can use for this Kd calculation. Now, we will discuss Ke value. Already I have discussed Ke value, already I have discussed that Ke value generally is called load factor. This load factor is 1 for reverse bending case. Reverse bending case I have already told you. This Ke value is 0.85 generally for axial types of fluctuating load or reverse load, you can say actual loading case, and for 0.59 generally for torsion case, already I have shown in first slide itself. Now, the another factor is there, that is called Kg factor. That Kg factor is called miscellaneous modifying factor. Here one of the miscellaneous very important effects which is related to welding, that is generally based on stress concentration factor. So, you can say here we will show you how this Kg value is varying if the stress concentration effect will consider. So, this it is observed that this Kg equal to 1 by Kf. What is Kf? Kf is called fatigue stress concentration factor, or you can say actual stress concentration factor. Here one thing you should keep it in mind, whatever the Kf here I am showing, this Kf have a value which is always greater than equal to 1. This you should keep it in mind. Whereas Ka, Kb, Kc, Ke and Kg, whatever the value I have shown, that value is always less than equal to 1. This you should keep it in. Generally for a mechanical component or actual component, its value always less than 1. This you should keep it in mind. Whereas this stress concentration factor Kf, its value is more than 1. How it is coming? For that some important notes here I am providing, because for how this Kg we are calculating for considering stress concentration effect, that is why we need to know some important information. That is why here I have written here some important notes is required. What are those important notes? That first of all we need to know what is stress concentration. You know this stress concentration means you can define as a localization of high stresses due to some irregularities or abrupt change of cross section. So, wherever there will be a abrupt change of cross section, there is a chance of rising of stresses. So, that rising of stresses you can say due to this localization of this high stress is called stress concentration. What I am telling, understand? Now, this stress concentration generally we can account by defining some stress concentration factor. That means, this stress concentration is accounted by defining some stress concentration factor. Some, not generally two different types of stress concentration factor here we will define. This first stress concentration factor generally is called theoretical stress concentration factor KT. It is also called theoretical stress concentration factor, or it is also sometimes called elastic, or you can say theoretical stress concentration factor, SCF I am writing. What is the definition of this elastic or theoretical stress concentration factor? It defines, that means the highest value of the actual stress near discontinuity, that means due to discontinuity whatever the highest stress is coming near the discontinuity, that stress value divided by the nominal stress obtained by elementary equation for minimum cross section. This you should keep it in mind. Or you can say, let us what happens here, if this is a specimen here I am showing which has a center hole, you see, which has a center hole. Now, this center hole diameter is d and let us consider weight of the plate is W. Now, due to this center hole, you see, now which minimum cross section is generally here effective, the minimum cross section will be effective only this thickness portion, correct. And now, you see, you know these things, due to this load here you see in this zone, in this discontinuity zone you see there is a high rise of stress is there. So, here the stress is this much, here due to the discontinuity regions once you come, here the stress rising its maximum. So, that is generally you can say sigma max, that you can write. Okay. So, this sigma max is the stresses near discontinuity. So, what is the theoretical stress concentration factor tell? It tell the sigma max divided by nominal stress. This nominal stress, how we obtain this nominal stress? This nominal stress we need to obtain, that is equal to generally considering the minimum cross sectional area of this specimen. Now, for this case, for the first case, what should be the minimum cross sectional area? So, sigma 0 you can say applied load P, this P is let us applied load, which is shown here, you can see in this first figure, this is figure number 1, here itself we have shown, let us this sigma what is the applied load P we are applying. This applied load P divided by here minimum section area we need to consider. Minimum section area means this, you see this diameter we remove, that portion material we remove. So, what is the remaining minimum cross section area is there, that we need to consider. So, that will be generally here the area here the cross sectional area you can say is equal to, you can say W, if the thickness of the plate is T, W into T, but here the minimum cross sectional area will be, you can say W minus that diameter which we remove into thickness of the plate. This you should keep it in mind. So, this is generally called nominal stress obtained by minimum cross sectional area. So, applied load divided by minimum cross section. So, I am giving another example. Let us consider a plate with a shoulder fillet. So, here let a shoulder fillet is there. Okay. Now, this specimen let us consider is subjected to load P. Here the diameter or diameter is d, width is d, here the width is small d, and let us consider this specimen have a thickness T. Now, for this case what should be the nominal stress sigma 0. So, here the sigma 0 should be always you should consider the minimum section area division. So, here applied load P divided by what it is called a small d into T, it should not be capital D into T, because capital D is the highest section area. So, but here we have defined this, here we should consider minimum cross sectional area. So, here the nominal stress we need to consider as P by a small d into T, that I am showing. So, you got the idea what is theoretical or elastic stress concentration factor, but in case of fatigue the actual generally reduction is endurance strength of a material due to stress concentration is less than the amount identified by theoretical stress concentration factor, because you see by considering this KT value, if we calculate the endurance strength, then whatever the endurance strength will get, that value will be what happens different than actual endurance strength value, what I am telling, understand. And if we consider generally, if we consider this KT value directly for calculating of endurance strength, then the actual reduction of endurance strength will be higher, because why it will be higher? Because generally I have already told you Kg is generally equal to 1 by Kf, or you can say stress concentration factor. Now, here instead of Kf, if you consider this Kt, then what happens, this Kt generally it is observed that this Kt value, here we are considering the highest value, because highest stress divided by nominal stress, that is why highest value. Here Kt term, then this Kg value will be less than the this if you consider actual what is called stress concentration effect, what I am telling, understand. That generally I am going to discuss what is this Kf now. So, that is why here I have written generally this Kt, whatever the stress concentration factor we are getting, it is the highest stress concentration factor we are assuming, but actually for fatigue life calculation it is observed that if you consider this highest value there, whatever the endurance strength you are getting, but in actual case generally your endurance strength is little bit higher side. That is why whatever the other stress concentration factor which you need to consider, that stress concentration value less than what is called Kt value. This you should keep it in mind. That means you can say this Kt is greater than is equal to Kf. Kt value generally always higher than Kf value. This you need to consider. Okay. So, that is why here what happens here, to find out the correct value of endurance strength, you can say what we need to consider, instead of considering Kt, we need to consider another stress concentration factor, that is Kf, what I am telling, understand. So, this is generally not applicable for finding out the actual or correct value of endurance strength. But what happens, there we can find out a relationship between Kt and Kf. How it is, that I will discuss in subsequent slide. So, that is why generally here we need to define two different types of stress concentration factor. One is called this theoretical stress concentration factor, or you can say elastic stress concentration factor, which I have already discussed. Another one is called the actual or fatigue stress concentration factor, Kf. Now, what is Kf? Kf is defined as endurance limit of a notch free specimen divided by endurance limit of a NOS specimen. I have already told you generally endurance limit of a NOS free specimen will be higher than the endurance limit of a NOS free NOS specimen. If a body have a NOS, its endurance strength definitely will be less. That is why this Kf, its value is greater than 1. What I am telling, understand? It value, if this NOS effect is there, then what happens, always this Kf value will be greater than 1. This you should keep it in mind. That means this stress concentration factor which I am discussing Kt or Kf, its value is greater than 1, but this Marine equation, whatever the different factor I have shown, that factor's value is always less than 1, or you can say less than equal to 1. Now, you see this Kf value, here some important points I have written, it generally depends on NOSes as well as it depends on the microstructure, or you can say grain size of the material. It is observed that if the grain size of a material is fine, then what happens, this endurance strength of fine grain material generally reduce its endurance strength more. What I am telling, understand? It is observed, that is why I have written, it is observed that there is a greater reduction in endurance strength for fine grain material, because fine grain material has more, you can say, this stress concentration effect than the coarse grain material due to this stress concentration. The fine grain has more stress concentration, this Kf value, than the coarse grain structure. This you should keep it. It is also depends on that grain size also. Now, to quantify or to find out the relationship between this theoretical stress concentration factor and actual stress concentration factor Kf, what happens, a separate factor is defined, that is called NOS sensitivity factor. Since NOS sensitivity factor is represented in terms of Q, here you can see. What is the definition of this NOS sensitivity factor? The definition of NOS sensitivity factor tells increase of actual stress, or you can say increase of actual stress over nominal stress, or you can say increase of fatigue stress or fatigue strength over nominal strength, that you can, or nominal stress divided by increase of theoretical stress over nominal stress. This you should keep it in mind. So, due to this stress concentration effect, what is the actual increase of stress is there over nominal stress, that divided by what is the increase of theoretical stress over nominal stress, that is generally known as NOS sensitivity factor. So, you can see if we consider Kt, so Kt you can write as sigma max divided by nominal stress, correct. So, you can write here sigma maximum in this case will be generally Kt into sigma 0. So, you can say here maximum stress coming due to this theoretical stress concentration factor is Kt into sigma 0. So, what is the rise of or increase of this stress? So, increase of this stress over nominal stress. So, sigma max minus sigma 0 you can consider as increase of theoretical stress over nominal stress. This you can tell us, that means this bottom terms which I am showing, this is actually you can say sigma max minus sigma 0. This is the increase of stress due to this theoretical stress concentration factor. What is sigma max here? Here you can say sigma max is equal to, you can say Kt into sigma 0 minus sigma 0, correct. Now, theoretical this is based on theoretical stress concentration factor. Now, what is the fatigue stress concentration factor? So, what is the sigma max here? Here the sigma max will be stress concentration factor into nominal stress minus this sigma 0, correct. So, that things only here, because this is the increase of, you can say, actual stress over nominal stress, correct, this is. So, that things here I have written. So, this is the difference Kf into sigma 0 minus sigma 0, and here we consider the next case we consider the theoretical stress concentration factor that based on that whatever the maximum stress you are getting, that is Kt into sigma 0 over nominal stress, that means minus sigma 0 we put. Based on these things, if you just write, your equation is coming like this. So, here this top side you can take a common of sigma 0, here you will get this Kf minus 1, and bottom side also you can take common of sigma 0, there you will get Kt minus 1. This sigma 0 cancel out. Based on this thing, generally you can get Q is equal to, so you can get this equal to Q. So, from here what you can write? Here you can write what Kf minus 1 is equal to, you can write Q into Kt minus 1, correct. So, from here you can write Kf is equal to 1 plus Q into Kt minus 1, this you should keep it in mind. So, your intention is to find out what? Your intention is to find out Kf value for fatigue life calculation or fatigue endurance strength calculation. Kf is required, not Kt, because if you will use Kt, you will get lesser value of endurance strength, but to be in optimum size generally you need to consider this Kf effect, actual effect you need to consider. If you use this Kf in your endurance strength calculation, then your endurance strength value will be more accurate, this you should keep it in mind. From this equation itself you can see. So, what we got? Q equal to, you know that Kf minus 1 divided by Kt minus 1, correct. From this equation I have also told you always this Kt generally always greater than equal to Kf, that means Kt value generally Kt value is more than Kf value if there is a NOS types of defect is there in your specimen. In case of weld generally there is lot of defect, lot of position is there in a weld which generally act as a NOS, what I am telling, understand. That is why in case of weld generally due to this different discontinuity defect, what happens, it is generally considered as a NOS specimen. That is why in a welded specimen generally this NOS sensitivity effect must be considered, what I am telling, understand. So, from this equation as Kt is greater than Kf, so from this equation itself you can see generally Q value is always less than 1, or you can say if Kt value is considered, if it is considered is Kt equal to Kf, at that time generally Q value will be 1. From this equation itself you can get the thing, what I am telling, understand. So, you see, so Q value generally always varying from, so whatever the Q value I am showing, it is generally always within a range of 0 to 1. Generally when it will be 0, here I have written, if here you see if Kf equal to 1 in this equation, let this is or this equation let us consider, here I am consider this is a equation. In this A equation, if we consider that which there is no NOS sensitivity effect is there, Q equal to 0, then you can say here Kf will be equal to what? Kf will be 1. So, that is why in this equation here I have written, if the material do not have consider any NOS sensitivity effect, then what happens, here Kf value is equal to 1, then your Kg, we know that Kg is defined as 1 by Kf. If this Kf will be 1, your Kg will be equal to 1, that means where you will consider no NOS sensitivity factor, your Kg generally based on this stress concentration effect will be equal to 1, this you should keep it in mind. Now, if you consider Q equal to 1 in this A equation, if you put Q equal to 1, here you see if you consider this Q equal to 1, then what are the things here you will get? You will get Kf is equal to your Kt. So, in this case generally when Q equal to 1, then Kt is equal to Kf. Here generally you can say here the material is fully sensitive to losses. That means, your Kf value can be maximum Kt, maximum equal to Kt. Generally Kf value always lesser than Kt value for actual specimen. This where generally there is some loss effect is there. So, that is why here I am written generally Q value varies between 0 to 1. Now, I have written also another very important point. Welding as such introduce a number of defects which generally act as a losses and which generally reduce the fatigue strain, because due to this loss sensitivity effect your Kf value is coming greater than 1 and then Kg value will be less than 1. Now, you know this endurance strain generally proportional to you can say this Kg. So, then as this Kg value is less than 1, AC value will be reduced depending upon this Kg values that Kg value factors, what I am telling, understand. Now, this modifying factor here I am showing generally this Kg, which is generally represented as whatever the actual stress concentration factor we have shown, that miscellaneous modifying factor which we used here for stress concentration effect, that we can write Kg equal to 1 by Kf. So, here generally for different types of welded joint I am showing some important Kf value, like what happens depending upon this type of weld joint, this Kf factors value have different and different, that you can say. Like for a reinforced types of butt weld, means you see what is reinforced butt weld joint. Reinforced butt weld joint means you see top reinforcement as well as bottom reinforcement. So, you know these things, in top side above the surface of the plate there is some bead height, you see, this is your B, this is called bead height. Okay. This is called top bead height, or you can say this is also have a name, that is called top reinforcement. Similarly, in bottom side also there is some bottom extension of sub weld material below the surface of this bottom plate. This is called bottom reinforcement. So, due to this you see this top reinforcement and bottom reinforcement in this butt weld zone, you see here generally in this zone, here I have shown, here generally it is subjected to some what is called stress concentration due to this abrupt change in this zone, butt weld zone, abrupt change is occur, here occurs some what is called stress concentration. So, due to this stress concentration for reinforced butt joint, generally a scientist whose name is C. H. Jennings, who generally established this Kf factor, which is equal to generally 1.2. So, C. H. Jennings calculated this Kf value for different types of weld joint. So, this Kf value you can directly consider in your SC calculation, that means endurance stress calculation depending upon the type of weld joint. Like for reinforced butt joint, its value is 1.2. For toe of the transverse plate weld, you see, always you should keep it in mind, transverse plate weld means let this is a plate, here you see if the load is perpendicular to the plate throat cross sectional area, you see here generally throat area is this, here will be the throat cross sectional area is this. So, here this P is acting perpendicular to the you can say throat section area, that is why what happens, as it is load is acting transverse to the plate, that is why this is called transverse fillet weld. This is example of transverse fillet weld. So, what is the toe of the fillet? I have already told you toe of the fillet means, let us consider this is a T joint. So, in case of T joint, let fillet well means which shape is almost triangular in nature. So, this, so you know from here to here this is called leg length, this is called throat thickness T, and this leg length corner point, whatever the corner point is there, this is called toe of the welt. This you should keep it in mind. Okay. So, here I have just shown little bit bigger way this throat thickness, this toe. You see in this toe region generally there is a chance of high stress concentration. What I am telling you understand, because here generally in this zone, toe zone, you see there is a sudden change of section is start. So, in this toe zone generally chances of stress concentration is more. So, that is why here we have written for these types of transverse fillet weld, you see transverse fillet weld at toe there is a fatigue stress concentration factor which is established by C.H. Jennings, that is 1.5. Now, parallel fillet weld means if the load is acting, let this is your fillet weld, you see this is one fillet weld, this is another fillet weld. If the load is acting parallel to the weld joint, whatever the weld is there, if it is acting, you see along the direction of the weld itself, load is acting here, you see this is generally called as parallel fillet weld. Parallel fillet weld means you see when the load is acting parallel to the direction of weld, you can see this is the fillet weld. So, for this case generally at its end, here generally stress concentration we consider is generally little bit higher side, its value is 2.7. Now, for T bar joint with sharp edge, now T bar joint what does it means? T bar joint means, let us consider that this is a inverted T. So, bar joint you know this I have already explained. Bar joint means here if you do the welding means you see in between two surface if the welding is done, then that is generally known as at the faying surface, you can say if the welding is done, that is generally known as bar joint. Generally bar weld is confined in between two workpiece cross section, this you can say, or else fillet weld generally exposed outside, this is called fillet which is triangular in nature, whereas bar means here this is one workpiece, this is another workpiece, here the welding this two workpiece is generally laying side by side, and what happens, it is welding is done in between this two faying face, what I am telling understand. So, here also you see in case of T bar joint, here you also this is called T bar joint, what I am telling understand, T bar joint. So, in case of T bar joint always you should keep it in mind this this Kf should consider as 2, what I am telling understand. By considering these different types of weld joint, generally if we go for calculating this S kg value generally calculated as kg is equal to 1 divided by Kf, what I am telling. So, depend upon your type of weld joint, you can use this equation and you can find out kg value. This kg value you need to use in that marine equation, what I am telling understand, and you can find out what is the actual endurance strain. So, this all about today's lecture. So, these are the references which I have followed for this lecture. Thank you.